Electronically, they're all the same electron structure. You rip one electron off of each one using the same process, fire them all in here, and you get different radii indicating, oh, there's different isotopes there. And carbon-12 dating, isotopic analysis, tracer analysis in medicine, all sorts of things kind of key off that. This is this idea, this is called a mass spectrometer. How do you get these particles to have a specific V? We'll talk about that a little bit later in this lecture. How do you get it to have a specific V? That's a trick that's also going into magnetism. All right. Now, let's take that same situation, which was cyclotron motion. Let's add something to it. So now V is some initial velocity. You might go back and call it a V0. And let's see, which way is the B field? B field's in the Z direction. Let's let that particle have a bit of velocity parallel to the B field. Still no E field present. No E fields at all. Well, the X component of velocity will still be the same. The fact that there's a V0x still leads to cyclotron motion. We just have to change everything to say something like mVx over r equals qb. Well, what does that V0z do? That means that this particle, instead of coming in straight like this, it's got a z component, which means it's like this. So my particle's headed off that way. Still, once it reaches here, it hits this field and it's going to start to spin a certain direction. But what's that z component going to do? It's not going to change. It's just going to continue to carry it out this way. So that particle is going to hit this field. It's going to start to circle. But as it circles, and by the way, this particle doesn't jump from circle to circle to circle. Once it starts circling, it would just stay in that circle. So our particle's coming in here, turn on the B field, and it starts to circle like this while it continues to move this direction. What's that shape? Well, that shape is called a helix. Think about slinky, a stretched out slinky. That's a helix. 36 minutes. Okay, lots of time. Turns out this is important in studying the effect that the Earth's magnetic field has on charged particles that come from the sun. Look at that helical motion again. I want to say the B field starts in line with the colored tiles. So it moves this way, moves this way. Hits the colored tile, and it's going to do this. Well, which way is the B field? It's the way I'm walking. And circular motion is around the B field line. So when charged particles come in and they interact with the Earth's B field, in essence you get a little more complicated, but it's basically that cyclotron motion. The charged particles move around the B field lines, but they also travel as well. And without going into details, because I just don't want to take the time, I didn't prepare any pictures for you to look at or anything, but one of the neat things that comes out of this is what I call the aurora borealis, the northern lights. And ask me some other time, and I'd be happy to show you a picture of that. Maybe I'll bring in a couple of slides for the next lecture and come back. In fact, let me make myself a note to that effect. It would be nice to show you a particle physics picture in an aurora picture and what's going on with those. So what I may actually do is append that to the end of this video. We'll see. Or I may wait until the next video starts. Okay, so a couple kinds of simple motion that we talked about in UPhys. Cyclotron motion, helical motion, we talked about that. Didn't do calculations with it, but that's okay. Now we're going to switch into something that's going to be a little more complicated, which will be our main thrust of this. Your book does one sample of this kind of motion. Well, your book actually does the helical motion, I believe, and they do it in a more sophisticated way that I've presented here. I just took cyclotron motion and added another dimension to it, which is a neat trick. To just add motion in an unaffected dimension, you can stretch something out over space. You shut off that z velocity, it sits there and spins, add the z velocity, it moves along. I guess you didn't get a very good picture of me walking to the back of the room, did you? Just thought of that. Oh, good video. Okay, third major idea here, and this will be really the last one. Crossed uniform fields. So now we're going to have both E fields and D fields, which means we'll have the full-blown Lorentz force. Did I say that's what this is called? This is called the Lorentz force. Q times the quantity E plus V cross B. Okay. Now, I'm going to redraw my axes for this. I'm going to say the z direction is down. The x direction is into the board. And so which way is y? If x is into the board and z is down, x cross y has to give you z, because y is going to be in this direction. So you can kind of see that as a little 3D picture. Think about that. It might seem like a clumsy arrangement, but it's the one I've got at the moment, and I didn't bother changing it. So when you think about a cube here, x, y, and z, of course, are three sides of a cube all meeting at the same vertex. So x is into the board, y is to the right, z is down. That's going to be the geometry that we use for this next portion of the notes. We're going to say that the B field is in the x direction. So the B field will be into the board. We're going to have an E field. Oh, back to there. Will be down. Sorry, mixed up my units here. In the E and M book, we use x hat, y hat, and z hat. Here we use I hat, j hat, and k hat. And I'm using my E and M notes, so I'm having to remember to translate as we go. And I'm going to shoot a charged particle into that cube, so to speak, into that region of space. That's a fancy word. That's not speed, it's velocity. So we're going to shoot a charged particle into that region in some generic direction. Some generic direction. There will always be a force in the z direction. No matter what direction I shoot that particle, there will be a force in the z direction. going to be equal to Q times E, because E is in the Z direction. No matter what direction we shoot, we'll always have an electric force in the Z direction. If we shoot straight down, it's a 1D kind of problem. If we shoot this way, then whatever, doesn't matter. Now, the B field is in the X direction. The Lorentz force is always, always, always perpendicular to B. Right? Catch that? If F is QV cross V, I mentioned this once already in this lecture. F is perpendicular to V, F is perpendicular to V. That's what a cross product does. The resultant of a cross product is perpendicular to both those vectors. So the magnetic force will, in fact, the electric force is always in the Z direction, right? Always, 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 because the electric field is in the Z direction. Nothing funky about electric. Magnetic, there is something funky, the cross product. I know that if B is in the X direction, F has to be perpendicular to that. So Fx has to be 0. There is no force in the direction of the B field. Why? The electric force can't push in the X direction, and the B field can't push in the X direction. So there's no acceleration in the X direction. So if there's a velocity in the X direction, initially, if there's a velocity component in the X direction, the X velocity stays constant. If we shoot the particle somewhat in the X direction, or glancing off into the board, that X component of velocity won't change. Well, we know how to add that in. That's just this idea that we talked about with helical motion. We just take our answer and then say, oh, by the way, besides whatever complicated motion it has, it's also traveling 10 meters per second in the X direction with that. So you take your velocity equation and you say plus 10 I hat to your final answer. It's very easy to deal with. So let's just say, for sake of removing a complication, let's assume Vx0 equals 0. And that means we'll never have any X component to deal with. If the X velocity is 0, the X position doesn't change for our particle. All right. Now, this stuff is not in the Fowles book, so I encourage you to, well, you'll have this video as documentation. If you'd like to take good notes, do that, because you're going to have to do something kind of similar in the homework with what I'm preparing to do now. So the electric force is Q times E in the Z direction. The magnetic force is Q times the velocity crossed into V. I know how to do a cross product. What are the components of velocity? Well, we just said Vx is 0. And then we have a Vy, and we have a Vz. There's the velocity in the y direction. Okay. Agree that that's my velocity vector? The velocity would be x dot, y dot, z dot. Well, we just said x dot is 0, so the velocity is 0, comma, y dot, z dot. So put that in. And then my b is only in the x direction. Ooh. B is only in the x direction. Let's take that cross product. You know you can factor scalars out of cross products, right? If it's a multiplier, you just put it in front of the determinant. So, what's the x component? 0. What's the y component? Q, E, Z dot in the y direction. And what's the z component? That minus that, minus Q, wait, that makes sense, Q, y dot. There's the magnetic force. So the grand total force is going to be Q, E, Z dot in the J direction plus, so let's factor the Q right there, Q times E minus E y dot in the K direction. See, my unit vector mistake crept up on me again. Q E Z dot, E minus B y dot. And that's equal to the mass times the acceleration, and y double dot in the y direction, and z double dot in the z direction. Why is it a I hat component? Because of this back here, right? There's no velocity in the x direction. Because there's no force in the x direction. I mean, the force, can you see that from the cross product here? The magnetic force cannot have an x component, and the electric force cannot have an x component. So the force cannot have an x component. So the x acceleration is 0, so why write that down? Let me write this as two separate little equations. Equate y components, m y double dot equals q v z dot, and q times e minus b y dot equals m z double dot. And I turn these then into acceleration equations. Y double dot equals q e over m z dot, and z double dot equals q over m. Factor the b out of it. Wait, there's no b in there. Yes, it is. It's just hidden. Okay. So it's kind of like, here's our core kinematics. We've got an equation for the y acceleration, we've got an equation for the z acceleration. It's still over here. It's still over here. Just barely, but it's still over here. V over R was omega. I don't think we can put this in the notes. Well, it's back earlier in the notes. So this is m omega is QE over R. So no. Oh, no, I used the R. QE over M. This is omega, my little squiggly balloon. QB over M. So instead of QB over M, I'm going to write that as omega. So let's go on to the next panel. Make something a little simpler looking. Eventually we can plug in what was the charge, what was the magnetic field, what was the mass. But for right now, we can express all of that, since they're just constants multiplied together, express all of those as a single constant that we'll call omega. Let me point something out to you real quick. But you can't add things to other things unless their units are the same. What are the units of y dot? It's a speed, meters per second. So what are the units of E over V? Meters per second. Do you know any fundamental, really important physical parameters that have units of meters per second? Speed of light. Turns out that E and V are related to each other through the speed of light. And if you've had modern physics, where does the speed of light show up? Relativity. E and V actually have a very neat relationship to each other because of relativity. I should go off on a tangent about that, but maybe I won't. It's going to turn into too long of a lecture with these. All right. So you go y dot equals omega z, and z double dot equals omega times e over b minus omega y dot. Right. These are called coupled differential equations. Andrew, I don't know if you've got to couple differential equations in Diffie-Q yet. I don't know if you do get to couple differential equations in a first semester Diffie-Q course, but we're going to get to it, even if Dr. Robin doesn't have to go there in his choice of curriculum. Okay? The y acceleration depends on the z speed. The z acceleration depends on the y speed. We haven't seen that really. It shows up, that does show up in quadratic air resistance, and maybe I mentioned that in the previous lecture. But other than there, we haven't seen that. And how did we handle quadratic air resistance? Well, in one dimension, there's no mixing of coordinates. You can't have coupled differential equations in one dimension. But when we looked at the Mickey Mantle baseball problem, if you started looking at that at all, and looked at the mathematical solution for that, they talk about the coupled differential equations. Now, fortunately, Mathematica is smart enough to know how to solve coupled differential equations numerically. So, we'll be able to deal with that in the chapter 4 homework, with that Mickey Mantle baseball type problem. But, we're going to solve this analytically. I'm going to differentiate the second equation. That says z triple dot equals minus omega y double dot. Because E over B is a constant, because these were constant fields. They didn't change. So more than just uniform, they're also constant. Maybe uniform includes constant as a subset. I don't know. And now, notice I've got a y double dot in both places. So let's take that, put it right there, and I get that z triple dot equals minus omega times omega times z dot. And I've uncoupled the equations. It's very much like two equations and two unknowns back in algebra class. You know, if you've got 3x plus 2y equals 7 and 5x minus 1y equals 3, you can solve one of the equations for x, substitute it into the other one, and get the equation in just one variable. That's exactly what we've done to uncouple these differential equations. We could have uncoupled going the other way. We could have differentiated this equation and got something for z double dot and substitute that in. I'm just following the method that I use in the Now, third order differential equation. Let's define a new variable. Capital Z is the same as z dot. Make sure you can tell the difference in my capital Z's and my lowercase z's. I would say stop me if you can't tell the difference, but you can't stop me. means big Z dot is Z double dot. And big Z double dot is little Z triple dot. So little Z triple dot is big Z double dot, and little Z dot is big Z. And you should recognize that equation. Maybe if I wrote it like this, d squared Z t squared equals minus omega squared Z. That's the simple harmonic oscillator, the simple harmonic motion differential equation. Second derivative is proportional to but opposite to the function itself. And we spent a fair bit of time on simple harmonic motion and damped simple harmonic motion and driven simple harmonic motion already this year. So this isn't damped, this isn't driven, this is just the core, the simplest simple harmonic motion idea. Pure mass on a spring with no friction, no damping, no driving, no nothing. So what was the solution to that? Same thing here. Big Z is equal to have various ways we could write it. You could write it like this. Big Z 0 cosine of omega t plus phi 0. Or we could write it in complex form. I'll go ahead and write it down just for completeness. We could write it as a complex quantity, and if I want to be really goofy and write it this way, maybe 0 complex, suck the phi out of this, put it there. Or, there's another way we could write it. Do cosine first or sine first? Yeah, do cosine first. If you remember, that's another way we could express simple harmonic motion. That's a way to get the phase difference, is by having sine and cosine split out separately and given different amplitudes. So you could solve, you go back in your simple harmonic motion notes and you could find Z0 in terms of C1 and C2. You could find phi naught in terms of C1 and C2. You could find C1 and C2 in terms of big Z0 and phi naught, etc. We're going to go with that right back here. Well, what is big Z? Big Z is Z dot. So I know what Z dot is. So now let's find Z. And just integrate. C1 over omega sine omega t minus C2 over omega cosine omega t plus some constant. And if you're clever, C3. Notice we had a third order equation. How many constants do I need for a third order equation? I have to integrate 3 times. That's 3 constants of integration. So that's just what I should have. Okay. I'm going to box a few of these equations. We have a to-go box. This is an important equation. This is an important equation. This is obviously going to take longer than an hour to do this lecture, but I'm going to go ahead and do it because I've got my lecture notes done. And I would rather finish them than start this again. Once I get one of these started, I'd like to just go for it. All right, so we solved for the Z motion. Now we need to look at the Y motion. Well, let's see, Y double dot. What I'm going to use. Y double dot. No, let's use this one. Yeah, let's use this one. Z double dots over omega. Is that right? Y dot is E over B minus Z double dot over omega. I got that just from undoing this equation. Could have used this one again, but then I would have had to integrate twice. If I go for Y dot, I only have to integrate once. This is a little z. A little z. This is a little z. Big z's are. There's a big z, 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 and there's others, but those are the kind of important big z's. Okay, so Y dot is E over B minus Z double dot over omega. What is Z double dot? Well, I know what Z dot is, so let's just differentiate it. What would I get? Negative C1 over omega sine omega t plus omega C2 cos omega t. Just a Z dot differentiated with Z double dot. E over B plus, wait a minute, we're differentiating, right? It has an omega in it. Yeah, sorry. The base cancel, plus C1 sine omega t minus C2 cos omega t. Check my notes. Z dot, no, Y dot, E over B plus C1 sine minus C2 cosine. That's Y dot. I'll put a blue box around that for them as well. So I've got Z dot, the velocity in the Z direction. I've got Z, the position, Z coordinate. I've got Y dot, the velocity in the Y direction. What's left? Just Y. You integrate that and we find Y. So, I think, oh, where's this panel? So we integrate. I could do this with integral signs and so forth. E over B